This topographical rendering traces the final trajectory of TWA Flight 514 over the Blue Ridge Mountains in 1974. Moments before impact, the cockpit voice recorders captured sudden, unexplained navigation instrument drift. The subsequent investigation of the crash site revealed anomalies that extended beyond standard mechanical failure. Investigators identified severe radio frequency interference, occurring precisely as the aircraft skirted the restricted perimeter of Mount Weather. The ensuing National Transportation Safety Board investigation inadvertently exposed surface antenna arrays, hardened satellite uplinks, and active subterranean emergency communications relays. An unmapped, hardened infrastructure was operating directly beneath the mountain. This 3D wireframe models the resulting Mount Weather High Point Special Facility, also known as Area B. The U.S. Army Corps of Engineers extracted 600,000 cubic yards of greenstone basalt to create 600,000 square feet of usable space, divided across 6 tunnel sectors. The chambers are situated between 300 and 1,000 feet beneath the solid surface level. Activated during the Cuban Missile Crisis, Mount Weather operates as the primary continuity of government standby vault for the United States Executive Branch, cabinet members, and high-level federal agencies. Mount Weather functions as a dynamic, closed-loop survival engine, engineered to neutralize kinetic, tectonic, and electrophysical threats within a single, integrated subterranean system. The facility is bored directly into pre-Cambrian greenstone basalt. This specific lithology possesses a rock mass compressive strength ranging from 220 to 310 megapascals. This finite element analysis visualizes the density. Blue vectors show greenstone basalt providing shock absorption, distributing a heavy surface load. However, this density creates a mechanical vulnerability. Under lateral shear stress, brittle fracture mechanics cause deep tunnel intersections to undergo structural spalling and deformation. Because Mount Weather sits adjacent to the Blue Ridge Fault System, localized tectonic fault shifts threaten large-scale rock deformation, vault settlement, and localized tunnel collapse. This schematic details the required structural reinforcement protocols deployed to counteract those forces. HW-125 steel arches and self-drilling rock bolts are embedded in C30 and C40 nanofiber reinforced concrete, which utilizes specialized basalt fibers to suppress microcrack propagation under heavy strain. By exploiting natural lithospheric density to defeat nuclear threats, the facility's structural integrity is inherently bound to the active, unpredictable nature of tectonic strain. The primary structural envelope is rated to withstand continuous overpressure wave loads of 100 to 300 pounds per square inch, equivalent to a 5-egaton surface explosion at a 4-mile slant range. When a surface nuclear blast detonates, its kinetic energy converts into a massive geoseismic shockwave that propagates downward through the geological media. This simulation models the blast attenuation physics inside the facility. As the cylindrical stress wave expands radially into confined underground spaces, its peak stress decays exponentially, governed by the damping coefficient of the surrounding elastic environment. To prevent the shock front from entering the complex, the access portals rely on dual 34-ton structural steel blast closure gates. These closure gates operate on hydraulic pneumatic actuators, maintaining a continuous nitrogen displacement pressure of 4,500 psi to lock the primary envelope instantly upon detection of a threat. The mechanical sealing tolerance for these massive hydropneumatic gates is configured to an exact specification, within plus or minus 0.5 millimeters. Defeating confined blast dynamics requires absolute mechanical precision. In a confined tunnel, a sub-millimeter sealing failure allows the overpressure wave to breach the gap, reflecting off internal walls and creating catastrophic internal shockwave amplification. Beyond physical pressure, high-altitude electromagnetic pulse weapons generate multi-phase threats capable of destroying unshielded solid-state electronics. This pulse propagates through 3 consecutive phases, E1, E2, and E3. The E1 phase is the most destructive, characterized by nanosecond rise times and extreme field strengths of up to 50 kilovolts per meter. The E1 wave induces massive, immediate voltage surges in internal conductors. This diagram models shielding effectiveness. Attenuation is the logarithmic ratio of incident to transmitted electric fields, relying on reflection and absorption. Engineering applies this math through advanced composites, like shotcrete conductive concrete,
utilizing a dense magnetite matrix directly behind a highly conductive protection layer. Systems like vermiculite geopolymers and touchstone Faraday panels can achieve exceptional attenuation levels, up to 50 decibels in the 14 to 18 GHz high-frequency band. To protect internal mainframes, Mount Weather must operate as a perfectly sealed Faraday cage. This introduces a severe bandwidth bottleneck. Achieving perfect electrophysical hardening with a minimum 100 decibel attenuation completely blocks internal electromagnetic emissions. This effectively blinds the facility by throttling ultra-high bandwidth external communication, forcing reliance on highly vulnerable surface-tethered antenna fields. To survive an exterior contamination event, the facility seals its pneumatic air intake valves and activates closed-loop chemical scrubbers capable of processing 120,000 cubic feet of air per minute. The life support matrix sustains an internal positive pressure differential of plus 0.05 inches water gauge, or 12.4 pascals, relative to ambient exterior pressure. This continuous outward flow physically prevents chemical, biological, or radiological infiltration. Sealing the complex creates a secondary crisis, the thermal dissipation versus infrared concealment paradox. Operating 6 2.5 megawatt heavy-duty diesel generators, carbon dioxide scrubbers, and oxygen regeneration cycles generates millions of BTUs of internal waste heat. This large eddy simulation tracks that thermal buildup. The facility must disperse extreme heat and continuous toxic gas evolution entirely within a sealed structural envelope to prevent internal temperatures from climbing to fatal levels. Standard industrial exhaust systems would solve this by venting the energy to the surface. However, venting massive thermal plumes breaches the facility's stealth, illuminating its exact physical position to orbital synthetic aperture radar and shortwave infrared detection. To manage this output, modernization protocols mandate the use of ultra-dense liquid nitrogen thermal mitigation units to mask geothermal heat signatures against orbital tracking. True atmospheric isolation completely shifts the primary survival threat from external atmospheric contamination to internal thermal overload and orbital exposure. This structural model of Mount Weather's lower western sector tunnels reveals a persistent natural threat: unmapped subterranean water aquifers actively intersecting the host rock mass. To prevent structural flooding, the facility runs continuous high-pressure dewatering pumps, extracting 800 gallons per minute every day. This constant physical maintenance requires exact automated oversight, governed by the facility's Campus Supervisory Control and Data Acquisition, or SCADA, system. As utility networks increasingly integrate 5G and wireless interfaces, industrial control systems become exposed targets. Virtual testbeds demonstrate that traditional security protocols can fail under passive reconnaissance or jamming, opening life support hardware to external cybernetic interference. Despite the massive external hardening, the realities of deep subterranean hydrology and modern network architecture create perpetual, active vulnerabilities that require constant automated mitigation. There remains one theoretical limit to Mount Weather's structural resilience: the phenomenon of complex overpressure wave refraction. This fluid simulation models a localized, multi-megaton groundburst sequence, detonating directly near the eastern ridge of the mountain. The kinetic energy converts into multi-directional shock waves that collide and reflect aggressively within the boundary layer between the host granite and the basalt. This trapped geoseismic energy amplifies, creating a localized resonance that mathematically exceeds the maximum axial load capacity of the facility's internal shock isolation spring assemblies. Under this extreme localized resonance, the primary greenstone basalt shell remains completely intact, while the sensitive electronic command arrays and life support matrices inside face catastrophic internal failure.